Okay. So in the last okay. In the last lecture, whatever we have done, that last lectures, whatever we tried to do, we learned basic components of the structure. We learned the different types of drawings. We learned how to do the positioning, basic positioning of columns. Um, After that, we have went through idealization. So we said first we need to know the drawing. We need to have the drawings. We don't have them. We need to develop them. And we learned what are the differences between architectural and structural. We have learned the differences between plan, elevation, section, and other things.
Excuse me, sir. Sorry for interruption.
Yes.
I'm having a problem here that only owners can send messages.
Okay. Just 1 second. Okay. Try now.
Yeah, now it's fine.
Amira, it can be for anything. It can be for the last class or whatever we have discussed today up to that time. Okay. So we started talking about the drawings, and after the drawings, we have talked about idealization, in which we try to draw the free body diagram for the different cases. Okay. And I have explained for
Sir,
you. Yes,
I cannot write in chat box.
you can. Everyone can now.
I don't think the problem is from my connection because I have class before this one.
Yeah, and it shouldn't be from my side as well. But that's all right. Anyhow, for those who are having an issue, you try now, Esmo. You try to go out and in once again. Okay. For those who are not able to write for any particular reason, if you didn't understand anything, you just open your mic and talk or speak it off that I didn't understand anything. Are you okay with that?
Yes.
Amira, once again, the pop-up quiz can be for anything which has been discussed previously or whatever has been or whatever is going to be discussed today till the time of the pop-up quiz. Okay, so you need to be what you call it. You need to be following up whatever I'm saying. Okay, and we have learned the different methodologies. We have learned in terms of loading. We said we have a point load, we have an area load, we have a line load, and I explained for you deeply. If you return back and you have seen the video that I recorded, you will be able to see that I explained for you the concept why in the slab it's kilonewton per meter square, what's kilonewton per meter for the beam, and it goes on. Now, after we finish our drawings and we go to the second step, which is idealization, it is going to be followed by analysis. So we have already our element with its loading. Okay, with its loading. The next step is going to do the structural analysis. And for the structural analysis, there are different options which are there, which can be used. You can do the analysis manually, or you can do them using a certain structural specialized software. Okay, I'm going to try to show you certain particular types of software that we might be dealing with throughout the semester. Now, my main intention in this particular course, we are going to do manual calculation, and we are going to compare it with the software as well. Okay, so we are going to use a lot of software. We are going to use a lot of manual calculation. Um, in the last class. Okay. So if you can see in this particular example, this is robot structural analysis, and if you can see here, we have different. Okay. We have different yield. You have studied yield line, right? You have studied yield line in the theory of structures too. Yield line. Okay. So you should be understanding. Okay, you should be understanding what is the what is the reason that we have different cases like here for this particular slab. If we go and see this particular slab, you will see that this particular slab, for example, okay. Okay, anyhow. Now if you can see here in this particular figure, you can see that we are having different types of okay, you can see that we are having different type of yield lines where we are having here, for example, where we are having here two trapezoidal and two triangles. Can you see this one? Two trapezoidal and two triangles. And then in this position, for example, we are having four triangles. And in this position, we are having three areas. Okay, we are having three areas. Okay. Now, any idea why this is happening? Do you know why this is happening?
Because of the shape of the slab, some of rectangular, some of rectangular and square.
Or sir, may be because of the distribution of load. Some of them are one-way slab, or some of them are two-way slab.
Okay. We'll have an example and then we'll see. So let's assume that we have two scenarios. Okay, so I have that this is 6 meters and this is 2 meters. And I have this is 6 meters, this is 2 meters. Okay. What do we have? This is having 4 beams. This is having only 2 beams. And we have another one. This is 6 into 6 meter. And then we have another one. This is 6 meter. This is 4 meter. Okay. This is only a recap. By the way, this is only a recap of whatever we have studied. Until now, we didn't solve the advanced answer. Okay. Now, can you tell me if this is case number 1, for example? Case number 1 is one way or two way? Case number one. Case number one. Is it one way or two way? One way. Case number two. Okay. Case number two. Is it one way or two way? One way. Okay. So how many areas will be there for case number one and case number two? You said, a lot of you have said that it is related to one way and two way. Now both of them. Okay, both of them, case number one and case number two, both of them are one way slab. Are they going to have different yield length, similar yield length? What do you think? No, 6 divided by 2 is more than 2. So that's going to be a one-way slab. So number one and number two are one-way slab. Are they going to have the same or different? Same yield line, different yield line.
Zero different. For case 1, there will be 4 areas, and for case 2, 2 areas only.
Okay, let's make it a little bit interesting. So I have added another one here. Now, how many areas now?
Three areas.
Okay, so to keep it simple, little bit, to keep it simple. Okay, to keep it little bit simple. You assume your slab to be paper. Okay, assume your slab to be a paper. You just understand here with me. Assume that your slab is a paper. Okay, and each slab is supported by beam, of course. Slab is supported by a beam in case of a solid slab. So each beam is representing one person who is trying to pull. So one person is trying to pull this paper from here. One person is trying to pull the paper from here. Another person will be pulling from here, and then the third one will be pulling from here. Okay. Now, how many persons are pulling? How many persons are pulling? Okay, you will see in that case, four are pulling. Okay? 4 are pulling. It means for me, if they try to pull that particular paper, each one of them is going to have a smaller portion of the paper. Okay, each one of them is going to have a smaller portion of that particular paper. Okay, now who is going to have bigger portion, who is going to have smaller portion, is related to how long is the part that I'm holding from. Okay, now who do you think will have a bigger part? A bigger part of the paper? Is it A? Is it A or is it B? Okay, A will be having more, and the main reason that because it's having more grip. Okay, he's having more area to pull the paper from. Are we okay? So it means if they start pulling, the paper will be starting to cut from here. Okay, the first cut is going to happen from the middle. After that, this will be linked to the corners. Okay, so this is going to be my failure. Okay, this is going to be my failure where we have two trapezoidals, two triangles. Are we fine?
A.
Okay. Scenario number 2, we have two beams. It means that one person is pulling from this side, another person is pulling from this side. How many portions will be there of paper? It's one paper pulled by two only. How many portions you will be seeing? You will be seeing only two. So half of the paper, because they are pulling from the same length. This is 6 meter, this is 6 meter as well. Okay, so half of it will go to this side and half of it will go to the other side. Okay. Now for case number 3. Case number 3, how many beams are there? 4 beams. So one person pulling from here, another one from here, another one from here, and then a fourth one from here. It means that there are 4 areas. Okay? There are 4 areas. They are pulling with the same length. It means that everyone is going to have exactly the same. So the failure point is going to be some point in the middle and then connected to the corner. The same thing goes for 4 and 6. We have 4 beams. Okay, we have 4 beams. So it will be cut from here. And then you connect it to the corner. Now if it's 3, here we have a beam here, another beam here, another beam here. But this is to be kept, this one was kept to be a cantilever. It means that there are 3 areas will be here. This is number 1, this is number 2, and this is number 3. Okay. Now how to draw how to draw this particular shape? The easiest thing is to continue the shape. So I'm assuming that there is a continuity here. We used to draw that this is a middle point of failure, middle line of failure, and then this is to be connected to the corner, this is to be connected to the other corner. Now I have just drawn, okay, if you remember, I have just drawn for the sake of continuing the slab. But this portion actually, this portion is not available with me. So this portion can go and be deleted. Okay, so if you go and see, this is going to be how the yield line is shown for me. Are we okay with the yield line? Okay. Going to the presentation once again. So if you can see here in robot structural analysis, you can see that we have different types of yield lines, okay, which will be shown by the software as well. Yeah. Another software that can be used is whatever we call it ETABS. Okay, we have ETABS safe. They are from the company of CSI. So that's another strong structural software available in the market. Okay, and this is an illustration. This is an illustration of a 3D and a 2D. So this is whatever we call it as a plan. This is whatever we call it as a 3D. Another example that we are going to use throughout this semester is whatever we call it as a Procon. Okay, so this is a Procon software which we are going to use throughout the semester. I'll teach you how to use it. Okay, and we are going to compare our manual calculation with Procon. This is some output of Procon. These are the bending moment diagrams. We'll come to that time and I'll explain for you what are the meanings of these bending moment diagrams. Because if there is any wrong input that you have entered in your calculation, you should understand it from the bending moment diagram. If you know how to read your bending moment diagram, then you shouldn't have a problem in terms of having a wrong input or not. And we'll learn how to do that. Okay. And this is representing the reinforcement schedule, where it shows you how many bars are going to be there in the bottom, how many bars are going to be there on the top, and it goes on. Okay. Another software we might be using, not we might be using, but we are going to use another software is whatever we call it as techleteds. Okay, whatever we call it as techleteds, where you can see here, we have done a design of a staircase in which all the calculation has been carried out as whatever you have studied in the college. Okay. Another software we might be using is whatever we call it techless structures. This techless structures mainly is used for the illustration of the reinforcement. Okay. Now you can see here how the reinforcement will look like. Always we had a problem in terms of imagining how the reinforcement will look like from one different element to another different element. Okay, so this techless structures is going to allow you to understand how the reinforcement will be looking like for any structural element. Okay, so these are the main software that we are going to tackle. There might be few more, and we are going to see them hopefully when we are going to solve for our own problems. Now, basic structural analysis says for you, for example, if we have a simply supported beam with a UDL, let's say simply supported beam with a UDL, it will give us a bending moment diagram which is parabolic with the value of W square over 8. Okay. Now, if you go and see, if you try to analyze this particular formula, okay, if you try to go and analyze it, you will understand. Okay, you will understand. Okay, you will understand that always when it comes to the bending moment diagram is going to be having an equation of beta multiplied by W multiplied by Lx square. Okay, beta multiplied by W multiplied by Lx square or L. We can keep it to be L for the meantime. Beta is whatever we call it as bending moment coefficient. Okay, so bending moment coefficient in case of UDL with a simply supported beam is going to be how much? We have the W according to this equation that we are having. We have our W, we have our L square, so L square will be coming here. So how much is the value of the bending moment coefficient? Our bending moment coefficient is going to be 1 over 8. Okay, our bending moment coefficient is going to be 1 over 8. The same thing goes for the shear. The only thing when it comes to shear, our general equation for shear is going to be beta multiplied by W multiplied by L. Okay, so we have two general equations that you need to know. First, moment is equal to beta. Beta is bending moment coefficient. Another beta here. Okay, another beta, but this is normally written to be beta V. This is the shear force coefficient. Okay, this is the shear force. This beta is shear force coefficient. W is the loading. L is going to be your length. Okay, so typical equation for any shear force. Okay, for any shear force, any regular shear force with the UDL is going to be beta WL, and then for moment it's beta WL square. Are we fine? Are we okay? Okay. Now, if you go and see here, if I ask you, for example, For a cantilever, what is your coefficient? Okay, what will be your coefficient? What is the coefficient? We have written that m is equal to beta multiplied by w L square, where I can use this formula for the UDL. So it's W L square is coming, and then we have only 1 over 2. So the coefficient of bending moment is going to be 1.1 over 2, and this is what you can see in your calculation here. Are we fine with that? Are we okay with that? Okay. Now we'll start a little bit playing here. Now, if you can see here, this is a structural analysis. This is structural analysis for a continuous element. Here we have used different software. This is robot structural analysis. This is, I believe it's Lendo. So this is bending moment diagram. This is a shear force. This is bending moment shear force. Okay. Are we fine? Okay. Now it's very important for me. It's very important for me that you understand this one, because without it we cannot proceed to the advanced RC. Okay. So whatever I'm going to try to highlight for you, okay, okay, I'm going to try to highlight the basics of understanding the support and understanding how the bending moment and shear force are drawn. Okay. So let's say for example, I have a continuous element which is having a UDL. Okay. So bending moment with a UDL. Now, do you know how to draw for this particular? Do you know how to draw for this particular sheet? Do you know how to draw the bending moment diagram for this particular sheet? Okay. Now, one thing that I want you to understand first before we proceed, okay, we need to understand something called continuous support and then non-continuous. Okay. I don't want to hear further fixed, pin, hinge, ruler. Okay, we are going continuous or non-continuous. Okay, we are going continuous or non-continuous. Now, if you can see in this particular example, continuous is wherever we say it, okay, is wherever we see it, continuous from both sides. Okay. If it's continuous only from one side, we call it to be non-continuous. Okay. So, for example, this particular support is considered now to be non-continuous. It has only continuity in one side, it does not have continuity in the other side. When we talk about continuity, is it connected to the other? Is it connected to another member from the other side? No, it's not connected. Are you okay? Okay. Now, what about this one? Is it connected from both sides or one side? Both sides. So this is whatever we call it as continuous. So this is continuous, and then we have this one to be non-continuous. Okay. So continuous, 3 supports are continuous, and then 2 supports, which are the outer supports, we have them to be non-continuous. Okay. Now the basic bending moment that we have, is for UDL and simply supported, okay, where we have it as a parabolic. And then the other scenario where we have it as fixed, okay, cantilever with this type of bending moment. Okay. Are we okay? Is it clear why we are going up and down, or it's not clear? Is it clear that we are?
Not clear. Not clear.
دكتور كيف حالك؟ مبارك. الحمد لله. شريك. الله يخليك. خلص معهم الكلاس؟ خلص من الكلاس ولا؟ عادي. زين اسفل. So الحين is it clear why it's positive and negative, why it's down and up?
No, Mr. Not clear.
So assuming, for example, that they have simply supported keys, Now, if I'm having it from both sides, can you see now this paper? So assuming that this is a simply supported piece.
Yes.
Simply supported piece. Now, if you apply any loading, the paper is going to bend down.
Okay.
If you apply any from the top, you will see that this paper is going to bend down. Are we okay?
Yes.
If I go and bring any load, assuming that this is a phone, you will see that this will bend in this direction. Are we okay? Are we okay?
Yes.
Second scenario. This is my pen. Now I'm having it fixed from one position. From one position, and I'm trying to apply certain loads. Now see what will happen to my support. When I am applying my support, up or down. You can try to
just go up.
If you try to apply a load here, you see that this support tries to go up. Are you okay? So that's why we have it.
Yes.
We have it here bottom, and we have it for the cantilever to be top. Now, if we can see, now this support and this support are non-continuous. These two supports are non-continuous because we don't have any other elements from the other sides. Are we fine? Now, this support is considered to be continuous. Okay, this support, since there is some kind of fixity, it's connected to something else. Are you okay? There is a difference. When I say simply supported, it means that this is my support and the pen is kept above me. Okay? So this is the scenario. This is the scenario of simply supported. Simply supported, the pen has been kept only above the pen, above the hand. Okay? When we talk about fixed, we talk about there is a connectivity here. Are we fine? Are we okay? Okay. So we have this one. We have this one to be non-continuous, and we have this case to be continuous. Okay. So what I'm going to try to do, I'm going to erase these, and I'm going to try to draw the bending moment diagram. So for the bending moment diagram, I'll just draw a line. Okay, I'll just draw the support. Now you see that this was an uncontinuous. This is an uncontinuous. It means they will act like this one. So they have a bending moment of 0. Then once again, this is ending up to the 0. Are we okay?
Mister, can you repeat this point again, please?
Okay. Now if you see, we said that this is an uncontinuous support because it's only continuous from one side. This is an uncontinuous support. A very good example of an uncontinuous support is simply supported. And when you go and see the ends at simply supported, the bending moment is available or equal to 0. Are we okay? When I say that there is no connectivity, it means that the bending moment is equal to 0. Are we fine? We'll come to it. Are we okay? Fine. Okay. So these ones, this one, this one, this one are continuous. If it's continuous, they are going to take the concept of the cantilever. Okay? If they are continuous, they are going to take the concept of the cantilever. So what I'm going to do, I'm going to try to draw a line above. Is it from, now when we take this span, is it continuous from both sides or one side? This support, is it from both sides? See, if we have it to be fixed, then it's only from one side. If we have it in this way, it means it's continuous from the first side and second side. Once again, we have two scenarios for continuous. Case number 1, where this is fixed only from one side. This one, we have it connected, the first one with the second one. So two sides. Are we okay? Are we fine? Okay. So if you see, since it's connected in this portion, I'll just draw a small cantilever as this one. It's connected for this side, so I'll just draw another one. Here, 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 here. And then finally, I'm going to connect the bending moments, which are 0, to this one. And then I'm going to connect these bending moments till they are completed. Are we clear with the concept? Okay. We'll have another example. Okay. Now, first thing, we need to decide continuous or non-continuous. Now, this one, is it continuous or not? This one. Is it continuous? Continuous. That's continuous. Okay, continuous. What about this one? See, just to keep it simple, if you have a simply supported at the end, it means it's not connected to something else. If you have it to be fixed, the fixed itself is showing some connectivity. Okay, is showing some connectivity. So this is to be continuous. this one to be continuous, this one to be continuous. Are we fine? Now, if I try to go and draw the bending moment diagram, this is my fixed. This is my first support, second, third. Okay, I just try to draw the bending moment diagram. Now this one, I just draw a line above, a line above, a line above, and then a line above. Now for the fixed, is it continuous from both sides or one side only? Because it's a fixed support. Fixed is always continuous. Fixed is always continuous. Now when we take this support, is it continuous from the left and right or only one? This support, is it connected? Does it have a member on the right and left or only one side? This particular member, this particular support, does it have a member on the right side, both sides? It's only one, right? It's only one. It's only one. So what I need to do, I just draw a line, and then the same case of a cantilever. What about here? What about this support now? Is it from both sides or one side? Both sides. So I'll just draw a small cantilever here, a small cantilever here. This one, both sides or one side? Both sides. So once again, a small one. Now this one, both sides or one side? Once again, two sides. Are we okay? Now if we try to connect, this will be looking like this. Now for this one, since it's cantilever, this bending moment at the end is going to be 0. So it goes to 0. Are we okay?
Mister, why the
Yes.
last one is from both sides?
Why what?
Why the last one is from both sides? The last support.
Is it the fixed one? You mean this one?
No, the last support.
This one? This one?
Yes.
It has a member on the right, it has a member on the left.
Okay.
Are we okay? This one is having left and right. This one is having left and right. This one is having only right. Are we fine? Are we okay? Okay. Last question, last example, and then let's stop. Now, what to do? How to draw the bending moment diagram? Okay. Now, if you try to try to put it into smaller things, it will be very easy. Now, first thing I need to decide here. This is an uncontinuous because it has only one side. The only case where it becomes to be continuous and it has one side is the cantilever or is a fixed support. This one is non-continuous. This one True that it has only one side, but because of the fixed support, it acts as a fixed, okay, or it acts as a continuous. Are we okay? So now what we see here, bending moment is 0. This bending moment goes in this way. This bending moment goes in this way. Okay. This bending moment once again goes in this way. And then here we have only from one side. Only from one side. Now if we try to connect, you see that this will go here regular because it's a UDL. This will go regular because it's a UDL. Now the situation will be different here. Okay, the situation will be different here. In case we know that in case of a simply supported with a point load, you will see that your bending moment acts like a triangle rather than a parabolic. Okay, so you will see instead of having it to be parabolic, I'll be having it to be a triangle. Are we okay? Life is too simple to deal with. Okay. So now, if there is no moment, here, we don't have a moment, it goes in this way. If we don't have a moment. Okay. Now, the only thing that we have a moment, and this moment, okay, this moment tries to take me up. Okay, this moment tries to take your element up rather than taking it down. It rotates, it takes you up. Okay, so what we need to do, okay, it will go as a regular parabola. Whenever you reach, it will go as a regular parabolic. When it goes to this position of the UDL, of the moment, it goes up because it push my element up, and then eventually it goes to a regular parabolic. Triangle part, this is what I tried to say. For a point load, if we have an element, I'm not sure whether I can. Anyhow, for a simply supported the point load, the bending moment comes in this shape. Okay. Now, if you see here, we have only a point load. For a UDL, it turns to be a parabolic. For a UDL, it turns to be a parabolic. For a point load, it's always going to be a point load. So instead of having a parabolic profile, we are having a triangle profile. For any type of drawing, if you know how to draw for a simply supported beam, for a cantilever beam, and UDL and point load, you should know how to draw for all the other cases. Are you okay? If you see now, it's only using the basics that we have done. The basic of UDL having a parabolic, the basics of the UDL having a point load, the basics of a cantilever with the UDL. That this is going to give me a negative bending moment in this way. So we try to see, if you see this portion is represented here. This portion, the bending moment is represented available here. And it goes on. Are you okay? This point load is represented here. Are we fine? Are we okay? Hello. So, so now you need to go. You need to go to your e-learning. Your pop-up quiz will be starting at 3 o'clock. So after 1 minute, and then it will be opening for 5 minutes. Okay. So you go to your e-learning. You find one question is available there for you. You need to answer it and then come back after 5 minutes.
Okay, Mr. Okay.
It will start at 3. It will finish at 3:05. Okay. It's available. It will open at 3 o'clock exactly. 3 sharp it will open. Yes. Try now. Try it now. It's open, my dear, in front of you. I'm opening it. It is available in front of you. I'm already opening the e-learning for you. It's open. Refresh your page. If you have not been added to the e-learning, then that's a different scenario. If you have registered late, then that's a different scenario. If anybody who is not having the e-learning, you just text it in the what you call, text it in the chat box. It's only one question. Already 42 has answered. for those who are not having the e-learning, okay, for those who are not having the e-learning, I'll just post for you the question. I'll just post the question for you in the Teams, and you can answer it over there. This is only for today. And then if you have not been added to e-learning, just inform me so I'll add you. Okay, so for those, once again, for those who are having issues in accessing the e-learning, today, since we are doing it for the first time, you can answer directly over there. Bushra, instead of replying or making a new conversation, you should reply in the same chat so we can see, because we cannot go outside of the outside of the chat for the video. Five minutes. Those who are having an issue, you might be finding the question. Okay. Those who are having an issue, they'll be finding the question available here. They can answer in the in the chat directly. Which option is the correct option? You need to check it out. This is only for today. The coming lectures, we are going to have it as fully e-learning. Okay. Are we fine? Everyone has finished? Everyone has finished the question? Okay, so we are going to continue. We are going to continue with our class. Hopefully that was an easy question for you. Okay. Now, going to continue whatever we have done. Okay. So we have explained. I have explained for you the bending moment diagram and how do we have it. Now I'm going to explain for you the shear force diagram. Okay, so if we want to try to draw the bending moment, the shear force diagram. Okay. First thing that we need to do. Yes.
مستر
Yes.
اسمه افتح الكويز السؤال بس شكل عليه كيف ترتيب.
Those who are having any issues, you can answer in the Teams. Only for today. Only for today, consideration will be happening. You can answer the question in the teams. I have already posted. Okay.
وين؟ يقطع صوتك.
In the teams. You can see it over there. In the teams, you open your teams. You can see that they have kept for you this question. You can answer directly. Everyone can see the question.
Okay.
Okay. Are we fine?
Welcome.
Now going for the shear force diagram. Now for the shear force diagram, it's a matter of going up and going down. Now this reaction is it going up or down? This reaction is going up or down? Reaction up or down? Up. This load, this UDL, is it going down or up? Down. Okay. Okay. So now if we go and see, when I try to draw the shear force diagram, because of the reaction here, I'm going to go up. Okay. Now because of the UDL, I'll keep on reducing because it's going down. So down, 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 down. I'll keep on going down. Now because of the reaction, I'll go once again up. Because of the UDL, I'll go down. Because of the reaction, once again, I'll go up. Because of the UDL, I'll go down. And then because of the reaction, once again, I'll go up. Are we fine? Is it clear? Why we are reducing? Because the UDL is not stopping at a certain point. So we reduced. The UDL is keep continuing. So we keep on reducing. Last scenario. Okay, last scenario. Once again, shear force is a matter of going up or down. Okay, up or down only. Now this reaction goes up or down. The reaction, if we keep drawing the reaction, it goes up or down? It goes up. So this is up. Your UDL is taking you down or up? UDL is taking you down or up? UDL will be taking you down. Reaction will take you, this reaction is going to take you up. UDL is going to take you down. Reaction is going to take you up. From this position, do you have any loading? Do you have any loading which will take you up or down in this location? In this location, do you have anything? Do you have any load going to take you up or down? So if nothing is taking me up or down, I just stay as I was. Okay. Now the point load is going to take you down. In this position, do we have anything? Any loading? Still. And then we have a reaction. So reaction will take you up. Okay. Are we okay? Are you okay with this? Okay, very good. If I asked you, for example, since you have already understood, try to draw for me the bending moment for this sheet? For this sheet. Can you tell me how to draw the bending moment diagram? Now you have understood everything. Yes. Any idea how to solve the bending moment for this sheet? This one. This sheet. This one. Okay. So what will you do now? How will you draw the bending moment diagram for this? First we draw. Yes. Do you want me to draw it for you? Shall I draw it for you? Okay. So now what do I have or what do I need to do? What do I need to do? I need to see my element. Now first of all of these are one-way slab. All of these are one-way slab. One-way slab is always going to have a major bending in one direction. Okay, and I'll explain further later. Why do we have one direction? Why do we have two direction? Why do we call this one way? Why do we call that two-way? Anyhow, for the meantime, what I need to understand, whatever you have done in design of structures one, you used to calculate only one bending moment for the one-way slab. You didn't calculate two moments. Okay. Now, if I go and try to draw, actually this particular figure is not something which is symmetrical as whatever we have done earlier. So I need to cut it into smaller portions. So case number one is here. So we have our slab supported by beam, supported by another beam. So this is case number one. Case number two, we have this support, this support, this support, this support, and then this support. That's case number two. Case number three is here. So we have one support, second support, third support, and then fourth support. That's case number three. Is the cutting clear? Whatever cut I have done, is it clear? Whatever cut I have done, is it clear for you? Okay. Now, evaluating them in terms of continuous and non-continuous once again. Now, now this is continuous or non-continuous? This one. This one. Is it continuous or non-continuous? We can see that it's not connected to something else. So this is not continuous. This is not continuous. This is non-continuous, 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 non-continuous. This is a continuous. This is a continuous. This is a continuous. This is a continuous. And this is a continuous. So if I try to draw the bending moment diagram, first case, bending moment is 0, bending moment is 0, and it goes to the variable. That's case number 1. Case number 2. Case number 2. What do we have? We have first support, second, third, fourth, and then fifth. This is 0 because it's discontinuous. This is 0 because it's discontinuous or non-continuous. This goes like this. This goes like this. This goes like this. And then we need to connect. So it's like this. Here, here, and then here. That is for case number 2. Case number,
Mr. First support isn't visible to us.
which support?
The first one. Here. For the second drawing, the beginning.
Okay, I'll just try to do it in
It's okay now. You deleted it.
now it's fine.
Yes, Mr.
So now you see. Okay, now if you can see for case number 3, what do we have? How many supports? We have 4. 1, 2, 3, and then 4. This is non-continuous, so 0. This is non-continuous. This goes up. Once again, this goes up, and then it goes to 0. Are we clear? Are we fine? Okay. Let us have another one. What about this now? So we have 2 scenarios. Scenario number 1, both of them are one-way slab. One of them is continuous, one of them is non-continuous. Okay, one of them is continuous, one of them is non-continuous. So if I try to go and draw a free body diagram, this is going to be my slab. This is my beam support. This is my beam support. So if I go and take it here, this support is available. This support is available. Now, if I go and try to draw for the second slab, this is my slab. There is a beam here. There is another beam. But there is another slab here. There is another slab here. So if I go and draw the free body diagram, you can see a support is coming here for the beam. Another support is available here. And then there is another slab. Now, how to draw the bending moment diagram? This is 0, this is 0, and then we have a parabola. Now, for the other scenario, this is continuous. So this goes like this, and then it returns. Are we clear? Are we fine with this one? You need only to use your basics, whatever you have studied previously. They're okay? Very good. Okay. If you see here, we have Ly, and then we have Lx. Now this is, of course, now for the one-way slab, always we draw for the shorter. So this is my shorter. Whatever I have done, I have drawn the line. This is my first support. This is my second support, and this is whatever is shown here. Okay. Another scenario, once again, I have drawn here. There is a support of beam. There is another support of a beam, but there is a slab here. There is a continuity here. So this is how it's shown for me. Okay. So always you need to draw the bending moment in the shorter direction. That's why it has been drawn to LX, not L1. Now when I go and draw the bending moment diagram, you will see that the bending moment will start from 0 and it goes here. The second scenario, it goes up, down, up, and then down. Whatever you are seeing here. Clear? Are we fine? Okay. The last slide and then we'll stop. Going to be this one. Now it says for us that this is a two-way slab. It says for us that this is two-way slab. Okay, this is a two-way slab. Now for a two-way slab, we have two bending moments. Okay? We have two bending moments. We have bending moment in X and we have bending moment on Y. So what I need to do, I'll just first take one line here. So this is going to be parallel to X. I'll just call it X. And then there is another one which is here, parallel to Y. So I'll just call it as Y. The same thing that I'm going to do here. One line is parallel to X. Another line is parallel to Y. Okay. So if I go and draw for X, this is my X. Okay. One support is available here, another support is available. So it's like this. This is for X. For Y, once again, just draw a line. There is one support here, there is one support here. So once again, I'm going for Y. Now going for the other shape, you can see if I start drawing for X, there is one support here, there is another support here, but we need to continue because there is something here, there is something here. So I just extended it. For Y, I have drawn the line. It is here for this support. It is here for this support. Once again, slab is supported by a beam. There is a connected slab here. There is a connected slab here. Now, if we try to draw the bending moment diagram, this is 0. This is 0. So this is my bending moment diagram. This is 0. This is 0. So bending moment diagram. This one, it has connectivity. So it goes up and then down. Once again, it goes up and then down. Are we clear with this? Are we fine? Okay. If you go and see, these are my simply supported. This is my continuous case. We have drawn the supports left and right for X and for Y. We have drawn for X and Y as well. Okay. Any moment here, it's going to be in this direction, whatever you can see here and here. For this, once again, it goes up. It goes up, down, and then up and down. And this is whatever you can see here. It means here we have one moment for X and we have one moment for Y. Here we have one moment for X, and this is going to be negative because it's up. This is going to be mx positive because it's down. This drawing is for Y, so this is going to be my. Because it's up, it's going to be negative. This one, because it's down, it's going to be my positive. So here we can see that we have 4 moments. 1, 2. This one is the same as this one. So 2 for X. This is for Y, and this is the other one for Y. Are we fine? By doing that, we have finished our class. Thank you very much for listening. Thank you very much for listening. See you in the upcoming class.
Excuse me, sir.
Yes.
Is my voice clear for you?
Yes.
Okay, I wanted to ask you about that. You have said that always try to draw the bending moment diagram in shorter direction. You mean that X direction?
One-way slabs.
It's only for the one-way slab. What if we draw it for the longer direction? It will be false. And why?
Wrong. Wrong. Due to the stiffness, always we have, first thing, those who are having a class, they can use. For those who are not having a class and they want to listen to this particular question, they can sit. Now, regarding when we talk about one-way slab and two-way slab, the main difference between them is how many major moments are there. Okay? So when we talk about one-way slab, it means that this slab bends in one direction, major bending moment in one direction, and then the other side is very minimal. Okay, while in two-way it goes in both directions. I'll just try to illustrate it for you using a paper. Now, this is a paper. This paper tends to be more of a two-way slab. Okay, the length and the width are closer to each other, so they are not more than 2. If you remember, we said it's two-way slab if the Ly over Lx is equal to or lesser than 2. Okay. So if you can see, this one to this one are not that, are not having that big difference. Okay. So this acts like a two-way slab. Now if you can see this one, this can bend in this direction, and you can see that it can bend in the other direction. So both directions are there. That's why we call it as a two-way slab, because it bends in 2 directions. Okay. Now the other scenario, let me see. Okay. The other good example of a one-way slab is this one. Now you can see for this particular ruler, we have 2 dimensions. One dimension is long, one dimension is short, which is representing one-way slab. One-way slab, it says for you, the long direction divided by the short direction goes to be more than 2. Okay. Now if you see here, this particular ruler can be bent in one direction. You can bend it in this direction, but you cannot go and bend it in the other direction. You cannot go and bend it in the other direction. Are we fine?
Yes, sir.
Okay. So 1 direction for one way and 2 directions for a two-way slab. I have already uploaded for you the presentation. So everything
Thank
will
you,
be.
sir.
Isa, regarding your question, I have already uploaded for you the presentation. Everything is going to be from the presentation. Regarding the handout, whenever it's going to be approved, you will be getting it hopefully. Any other question?
No, thank you, Mr.
Okay. Because the shorter is having more stiffness. Okay. Now, once again, if you go and see here, along the shorter direction, it will only bend. Okay. So the bending is happening in this scenario, okay, along the shorter direction. While the other way, if I take it from here, I cannot bend it. The other side, I cannot bend it. Along the y direction, I cannot bend it. The bending is very, very minimal. Okay. Hopefully that's clear. You take a ruler and you will understand the concept of one-way slab. Thank you very much. See you in the upcoming lectures.
Thank you, Mr.